Hi, everybody. Thanks for coming. My name is Johnson-Roberson. I'm a professor at the University of Michigan, and I'm going to try to talk to you guys today about where, from my perspective, we are in terms of autonomous driving, and try to give you a bit of perspective from what I think of as more of the academic side as opposed to the commercial side, and thinking about what do we think works, where are we at, and sort of beyond the marketing bits. So I'm hoping that towards the end, or if you have questions during, please let me know, and we can try to figure out ways of getting to them. So who am I, and why am I telling you about self-driving cars? Well, I got into this actually a really long time ago in the world of self-driving cars, for me at least. So when I was a much younger man, at Carnegie Mellon as an undergrad, actually, I got involved in the 2004 DARPA Grand Challenge, the first one, the off-road one. And so this is a young me. If you want to know what 15 or 18 years of working in robotics does to you, you can see the haggard person in front of you. That's what I've become. But that was a really transformational moment, I think, for at least the commercial side of the industry, because that turned into the urban challenge, which turned into a number of these large-scale commercial efforts that we see now. And so one of the things I want to do is kind of provide perspective that, while it's in the news quite a bit now, this is actually a thing that's been going on even before I got into it and before it was sort of on anyone's radar. So that was the vehicle that we used back then. And why I like to highlight this is that sort of one of the things I think is interesting is that over 15 years, a lot of the technology hasn't evolved as much as we would like to think. In some ways it has, in some other ways it hasn't. So that vehicle had many of the same sensors that you would see on sort of the current self-driving cars. They were just in an uglier, bigger, sort of more expensive, and slightly less accurate form. But out there on the front, that white thing is a millimeter wave radar. Those sort of gray and black boxes up on the edges of the vehicle, those are old planar LiDARs, so those are laser rangefinders, much like the kind of modern, more high-resolution laser rangefinders we have now. And that thing that's a dome on the top with a glass on the front of it had actually a long-range laser rangefinder, and that one could see about to 200 meters. And that's sort of really where we are now in three-dimensional LiDARs in terms of the max distance that we can see. Maybe you shouldn't listen to me because we rolled that vehicle over about a week before the race, which was tragic. We were able to get to the race and go the furthest of anyone, but weren't able to complete it. So where has that kind of gone, or how's that evolved? Well, so again, I wanted to highlight that sort of, at least my intro into it was really not the beginning or the history of where this actually started. So as far back as the 1960s, RCA had a project where they had a vehicle that used embedded wires in the road itself. And you could call one of the really earliest self-driving cars. And so that vehicle was able to go with one modality, just that magnetic sensing in the road. And then they had a human controlling the throttle, but was able to do what I would say is sort of lane keeping and sort of get out there in front and sort of set the flag for what we could do. Later on, there were numerous really, really important efforts that I would argue did a lot of the things that we consider now and things that are off the shelf. So particularly want to highlight sort of the NavLab 5, which had one sensor, which was just a camera, and that was able to go from Pittsburgh all the way out to California. And so one of the things that I think this highlighted for me when we were thinking about this in history and where we are now is there's lots of discussion of that, we're almost there and the cars are going to be on the road now. But that vehicle we had in the 1990s really does what the Tesla Autopilot does now. And so to think of that as a full self-driving car, you can go back to talk to the people in the 1990s and why that never turned into a product that you were in any time between the 1990s and now. And there are some real fundamental challenges to the safety and to the reliability of systems like that. I think that is what we are seeing, this long tail of challenges that exist. And so, you can get into any of the demos that, you see at the tech shows here, or any of the companies will take you in. You'll get in and you'll get a ride that is actually, probably I would argue, even better than what the NavLab 5 was capable of doing. But one of the things that's really important to keep in mind is there's still a reason why there are safety drivers in all those vehicles. And we'll talk about that in a little bit. That sort of evolved into kind of when I got excited about it, which was that Sandstorm vehicle in sort of the early 2000s. That was beaten in the next race by Stanley, which was Stanford's vehicle. And again, one of the curves I want to show here is just the complexity of the sensor data and the richness of the sensor data keeps going up. So Stanley had 8 sensors over 3 different modalities. Sandstorm had 7 sensors over 3 modalities. And then later in the urban challenges, so the Stanford Vehicle Junior and then the CMU Vehicle Boss had 18 sensors in 3 modalities. So one of the things we're seeing as this technology improves is we're able to combine many of the sensors that had to be independent sensors into 1 or 2 units that do multiple of those tasks. So a good example of that is automotive radar. There used to be needs for multiple automotive radars to look at different frequencies and also look at different ranges. A lot of those have been combined into what we consider now one sensor. So you can buy an off-the-shelf automotive radar that does close distance and medium distance scanning, long distance scanning, et cetera. Same is true of LiDAR. The LiDARs that we used to have 7 or 10 of on the vehicle have now been combined into many receivers within one LiDAR. And so again, that buys us the ability of making these things more compact, making them look more like production vehicles. But one question that still remains, right, is that data sufficient to allow us to drive? And so again, I'm not trying to be overly pessimistic here. I'm going to talk about some of the reasons why I think it is going to be possible and what we're capable of doing. But I do want to kind of provide some counterbalance to all the marketing that we see out there. So that was that Stanford vehicle that won the second race in the off-road challenge. This is the CMU Vehicle Boss. And again, you can see that there's just a lot of things that start to look like almost what we have now. So like what you see on the top there, that gray spinning thing, is a spinning mirror LiDAR that sort of has evolved into what you see on the vast majority of the kind of modern production level vehicles, particularly Google's and others. At the University of Michigan, there was a long history of professors before I got there doing work. So several others, including Ed Olson and Ryan Eustace, worked on these platforms, both at Michigan and at their previous institutions. But by the time I showed up, we had been handed a vehicle that was coming off the production line from Ford, and they were able to give us something that starts to look like a real car, doesn't have as many sort of sensors hanging off of it. The only thing that kind of distinguishes that from what you would buy off the lot, again, are those spinning mirror LiDARs that you see on the roof there. And even that technology is getting better. So we're now seeing evolutions to what will be solid-state LiDARs when they hit production with those. It'll bring them down in terms of compactness, and we're going to get them embedded in different parts of the vehicle. So again, it looks more like a production vehicle, less like an experimental test bed. So again, that's that vehicle, and you can see aside from those LiDARs, there's not much else to distinguish it. There's a little GPS antenna up there, but all that's getting embedded in the vehicle. And that's because we really do know how to make cars, right? You know, that is one piece of engineering that we've understood for 100 years. And so if we decide what sensors we want and we figure out how to make them at a production scale, we can get them embedded in a vehicle. The cars you take off the lot today actually have many sensors that weren't even in there 10 or 15 years ago to do things like lane keeping assist, to do things like automatic emergency braking, to do things like blind spot detection. And all those are sensors that at one point were experimental research sensors that then got embedded into smaller and smaller and more streamlined versions of that within the vehicle. So at the University of Michigan, we have a nice test track, which has been really cool to use. And so this is some data gathered by a colleague of mine, Ryan Eustace. But why I like to show this is this kind of gives a quick overview of sort of why and how most of the modern self-driving cars work. So that's the test track we use. And this is a high-definition map of that test track. So the vast majority of cars that are driving around today, level 4 or fully autonomous cars that at some point hope to remove the safety driver, have a map that looks like this. And what's interesting about a map that looks like this is it means they have all of the LiDAR returns or all of those laser returns of the entire environment. Let me see if I can pause this without breaking it. Nope, I can't. Oh no. All my well-laid plans. No. Okay, I'll just talk over it while we try that again. So those lasers, all those returns of those lasers give you this high-definition map of the environment. And that's where all the buildings are, but more than that, it's also where the intensity of the road is. And so you can see all the lane lines, you can see everything on the road there. And so when we zoom in here, you're going to see all of the things that you would see on the street, but they're really, really intense. And because what that's looking at is actually the reflectivity of what's on the road. So it's actually not the color of it, but the reflectivity, which is sort of a function of color and incident angle and some other things. See those blue points, what those are live returns from the vehicle. So the vehicle's taking data live, and what it's doing is it's matching that data to that high-resolution map. And why that's really, really important is what that enables is the vehicle to localize or figure out where it is in the world to a fidelity that's much higher than GPS. And that's important because GPS is probably accurate in downtown urban areas to 2 to 5 meters. In wide open areas, you can get it down a little bit further if you add other sensors in. But what's important about that is that's not enough to keep you in your lane. That's not even enough to keep you out of the intersection. You know? So you would pass through red lights. You would be driving against traffic. And so to figure out where you are in the world to a couple centimeters, you need something else. And the primary way people have been doing that, at least for the last 7 or 8 years, is using these really high-resolution maps and then figuring out where you are in that map. There's a couple things that make that really challenging, though, because it means that map has to be maintained and kept up to date all the time. And for most of the approaches, people are looking at things like ground plane-based localization. So what that means is they're looking at the ground and trying to figure out, okay, how do I match what I'm seeing live from what's on the ground? And if it's snowing or if it's raining, those are two things that obscure what's on the ground and in fact change really drastically the type of returns you get. And in fact, in standing water, you get almost no LiDAR returns. And then additionally, snow or rain or changes, construction sites, building changes, foliage, all these kind of things make it really difficult for the vehicle to figure out where it is in that map. And so one thing that makes that mapping approach really robust is that it tells you where you are in the world really, really accurately if the map is good, up to date, and you can see it. But it does a really, really poor job, and the vehicle's really fragile if that map is not up to date or there's something in it that it doesn't understand. And so one of the challenges, not just from scaling the vehicles in terms of understanding the world, but also from scaling it in terms of the mapping challenge, it would be incredibly difficult to think about how we would scale this to really, really large cities really, really quickly. And people are thinking about this. It's an open research question, but at least in its current form, there are some challenges to what we're doing there. So we were trying to understand some of the other challenges that I think are going to be really, really important to deal with in the coming kind of couple of years. And so we set up a vehicle at a set of intersections, and we've been looking at trying to understand pedestrians. Because in my opinion, one of the greatest challenges to getting us to having cars deployed with no safety drivers in urban areas is people. And in fact, one of the reasons why I think highway driving, or I would consider highway driving with full autonomy, really an effectively solved problem is that you don't have pedestrians. You don't have anyone that's unprotected. And if you think about what the biggest risk is with autonomous vehicles, it's a collision between a person that's not in a car and a car. Because it turns out that we're actually really good at making cars fairly safe. And your chance of getting seriously injured if you were to be hit from behind or even run into something in a car these days is actually fairly low. We have airbags, crumple zones, the frames have been redesigned. But if you're a pedestrian walking around, that's still a massive issue, right? So if you get hit by a car as a pedestrian and you're not protected by anything, the chance of something really serious happening to you is very, very high. And so if we're going to have cars in urban areas, that really brings in the fact that you're going to have people that you can't control, people that you don't know where they're going to be, and you're going to have to deal with them. And so that's what I think one of the biggest open challenges is. So we've been putting together a data set that looks at this exact problem. And what we want to do is understand what happens and what are the behaviors that people have in intersections. And so again, we set up at University of Michigan, which is sort of an urban campus. And so you get lots of students running around doing lots of interesting things. And you can see there's snow on the ground here. But again, what we're interested in is fitting models to that and trying to understand what people are doing. So you can see a guy there is grabbing a cell phone. You can see that people are walking holding bags, putting in earphones. And we've been fitting models to that, trying to understand if we can understand how people move, where they're going to go, and what they're going to do. And so ultimately, what we think is if you can make predictive models of that with some level of efficacy, that you're going to end up in a position where you might be able to start having cars that drive around people with enough of a safety margin to ensure they don't get hit. And so you can see that this is just one intersection, but the number of people you end up having to track and deal with becomes really, really high really, really quickly. And so again, thinking about how far in the future you can predict where they're going to be becomes really important, because one of the things that limits our ability to drive is that when you're driving, you make some assumptions about that nobody's going to jump out in front of you within your stopping distance. With those assumptions, if you see somebody that's not paying attention, or you see somebody that is really young or not really aware of the road, not looking at you, those are things that you factor into the way that you drive. And if you don't do that as an autonomous vehicle, well, then you may make a decision that while if it was a different scenario would be safe, becomes unsafe in that context. Okay. So one of the things we've been doing is using slower, lower speed vehicles to test things out, just under the risk that we can take higher risk maneuvers, we can do things without the risk of hitting anybody and making things bad. Okay, so how hard is this as a problem? Well, so one of the things that I think is going to be the big limiting factor is that we're dealing with this idea of driving, but driving is this really diverse set of activities. So it's not just one thing. When we're driving on highways, we're driving in city streets, we're driving on big roads, we're driving on small roads with pedestrians, without pedestrians. But we are, I think, in a new era now with respect to sort of where technology is, and so people are arguing that this is sort of going to be the turning point. And so let me make the case as to why that might be. So people argue that there have been two big advances, or I would argue there have been two big advances that would drive our ability to have this be the time now where we're actually able to build self-driving cars without safety drivers that are deployable sort of over a wide scale. And those two big drivers have been higher sensor fidelity and higher sensor quality. So what you see there on the left is a high resolution LiDAR, and that was sort of one of the first ones that was really, really could see much further and had much greater fidelity than previous sensors. And so that was a big step forward. And they keep getting better and better. Now we have LiDARs that, again, removing the spinning mirrors that have higher resolution, higher angular resolution, so that means the space between the points is smaller, and then they can see further, so their range is much longer than they used to be. And those are the things that I think are going to be really important for pushing this forward. The second thing is that there's been huge advances in sort of computing power. Not exactly in the way that we would have thought, maybe even 10 years ago, but what we've realized is we can do many tasks in parallel at much faster speeds than we used to be able to. And that's sort of been driven in most part by GPUs. And so graphic processing units, the things we use to play video games, have proven really effective at solving other types of problems that involve big matrix operations really, really quickly. And so that kind of big leap in sort of graphics processing power along with sensors, I think, has been something that's been really important. Now, one of the things that I want to push back on then is also that people talk about this as some big bang of artificial intelligence, and there's been huge leaps forward, particularly in deep learning, which has been one aspect of machine learning that has seen huge advances really over the last 5 or 6 years in ways that couldn't have been anticipated. But the pushback to that is that it's not clear exactly what problems that is solving that the self-driving domain really needs, or what it is solving in exactly the way that it needs. So I'll talk about some things that it's really good at and some things that it's not really good at in a little bit. The second reason why this is really hard is the kind of nature of the problem we're trying to solve. So this is a graph of US vehicle fatalities per year. And if you look at this, it is something that really makes you take a step back and think we are solving an important problem here, right? So what this graph really shows is that we still have over 30,000 per year in the United States from auto fatalities, from auto injuries. And that would be the equivalent of a 747 falling out of the sky 5 days a week. And this is the number that companies talk about. This is the thing that they hit you with. And this is the thing that really tugs on your heartstrings and say, this is something that's important that we should be solving. I want to flip that number on its head just a little bit and kind of talk about something that we don't think about a lot, but that we're actually getting much safer as drivers in some ways. And so what this is a graph of that same information, but this is a graph of the fatalities per 100 million vehicle miles traveled. So to put that in context, what that means is that if we travel 100 million vehicle miles, how many fatalities do we expect to happen within that? And to put that in even greater context, none of you in this room will probably, if you're lucky, ever travel 100 million vehicle miles in your cars. Probably nobody you and all your family, probably if you combine them together, won't travel 100 million vehicle miles. And so that means on average, you would expect not to have a fatality occur to anybody. On average. Now, the challenge with that number, also to put in context, right, is that's not an evenly distributed number, right? That's the average. And so what that doesn't take into account is impaired driving, so that's drunk driving, other things like that. It doesn't take into account young drivers. So the distribution of where those fatalities are occurring is actually really non-uniform. So if you take an average adult driver, they're actually fairly safe. If you look at the whole distribution, you end up with a lot of other issues. But where we are there is we're down close past 2010, and we're a little bit over 1 fatality per 100 million vehicle miles traveled, which is an incredible distance to travel. And so what we can really attribute to that is this big drop really corresponds in a lot of ways to these adoptions of safety technologies. And so some of those adoptions are things that really make sense, that were intuitive, and then some of those other ones are ones that we really thought about from an engineering perspective and put into place. So the simplest ones were we didn't used to have traffic lights, so people would drive around, there were no traffic lights, as before I think most of us were born, but that was a time. And then we also didn't have speed limits. And the introduction of modern speed limits, we saw big drops in fatalities. Seatbelts, again, helped quite a bit. But one of the things I like to point out, which I think is interesting and people talk about, is that there tends to be an uptick after we introduce a safety technology. And what people who study this think is that, or what they've kind of trying to show, is that people get a safety technology like seatbelts, and they think, oh, I'm much safer now, so I can drive faster, I can drive more aggressively, and I can do things that I wouldn't have done if I didn't have a seatbelt. And so it takes a little while for the equilibrium to balance back out and get back to the point where that safety technology that we know is helpful actually has benefit. Things like airbags, ABS, electronic stability control, and we're getting down to this asymptote now. So, one fatality per 100 million vehicle miles is quite a lot. And so this is now out of date. They've gone even further now, but this is how far Waymo's gone. This was back, I think, in 2019, early 2019, but they'd gone 10 million vehicle miles. Now, there's a lot of debate around sort of what is the right type of miles, what are the number of miles that count, all these kind of things. But to put this in perspective, right, they'd have to keep driving at this rate another 10 times to get to the point where you'd expect at least one fatality on average. But if you think about having statistical significance, or what is the ability you would have to prove that you're driving more safely than human beings, you couldn't just drive the same amount human beings would and say, oh, we didn't have a fatality, great, we're safer. Right? So there really is some challenge around how do you test and how do you understand what is safer than a human being. And I think more importantly is that traveling, if we're only having one fatality per 100 million vehicle miles, that is a huge hurdle to pass. It means that we have to have a system that is incredibly safe. And incredibly safe because it means that if we're going to replace humans with that system, the number of vehicle miles they would have to travel before you would expect something bad to happen would have to be significantly higher than what humans are doing, which is already a really, really large number. And one of the things I'd like to point out is that we've already seen fatalities from this. And so one of the things that I think it's important to keep in mind is that when we think about the way that we think about the regulatory environment or testing in this kind of domain, we need to think about the real human costs of this, right? Because Waymo had not even traveled close to 100 million vehicle miles, and they've already killed somebody, right? So I think it's important to bear in mind that there are big safety advantages that could come if we really do figure out how to do this, but that is a huge, huge challenge, and particularly the statistics of doing this are really, really difficult. Another thing I think is important to point out is that a lot of those fatalities occur when driving is really hard. Those fatalities tend not to occur when driving is really easy. So if you're driving in sunny weather, like let's say Nevada, Arizona, California, where lots of the testing is done, and you're not seeing rain and you're not seeing adverse weather like snow, you're not seeing the cases that are really hard. And I think that really points out in many ways sort of why I think this is going to be a thing that's going to be very difficult to do in some cases. So to have it touch everybody's lives in the way that we want, we're going to have this rolled out in many places where it doesn't exist right now, or it's not even being tested right now in many ways. And those are going to be the cases when there's a snowstorm, that's when fatalities occur. When there's a thunderstorm, when there's a lot of rain on the road, when things are moving really, really quickly, when there's something weird happening, that tends to be when humans have a hard time dealing with this. And to design a system that is effective or is better than that is going to really require us thinking through what are the testing regimes that we need to implement? What are the things that we need to be trying out to figure that out? Another great example is night. Lots of fatalities, particularly pedestrian fatalities, occur at night because obviously people are harder to see at night than they are during the day. And so again, we see lots of testing during the day. We see lots of examples of how these cars are working well during the day. But that Uber fatality occurred at night. And it's a great example of why those cases, or why driving at night, or why driving in hard cases is the things that we're going to have to deal with. So another major argument that's made around this is the notion of economics. And so I kind of want to talk about where the economics around self-driving come in and why people are excited about it. Well, so there's this idea, this is a self-driving shuttle driving around a campus in Switzerland, I believe. But there's this idea that we can move people from place to place, and that's a thing that costs money. And so that if we can do that, or we can share that resource in some way, we can make this more efficient, right? And so why people really think about this in some ways is that right now, these are sort of the cost per mile of different services that are offered, right? So taxis average out around $1.95 per mile. Now, Uber and other ride-sharing companies average out at about 75 cents. And one of the things that's interesting, this slide's a little out of date, but what it seems like now from the public filings is that that number comes from fairly heavily subsidized takeover over markets. So the question is whether or not when Uber stops subsidizing, or when these ride-sharing companies stop subsidizing, basically making the fares artificially low to take over markets, whether that number gets up closer to taxis, or in fact is at least higher than where it is now. So that big cost savings we're seeing from ride-sharing over where it was from taxis may be, to some sense, artificial. Now, there's a lot of different studies on this. People come up with different numbers, but there is pretty widespread agreement that if you're able to remove the driver, which is the dominant cost in the ride-sharing model, you can bring that cost per mile down significantly. The big assumption here is that thing that I just said, that you're removing the driver from the vehicle. And so this is not a deployment of safety technology now. This is a deployment of technology that does not have drivers, so truly driverless technology. And so to do this cost saving or have the economic benefits that people are talking about, you would have to remove the driver. And this bears out the point that that is the thing I think that is going to be the hardest to do. So I read the news just like you guys, and one of the things that really came to me is that, a couple years ago, I was like, wow, we got a lot further than I thought, right? So I would see these stories, and I was like, wow, in my lab with my students, I really can't make anything work nearly this well, but I guess they got a lot of money, so, maybe I'm just a sucker. And my students would be like, man, I'm really disheartened, like they solved it, they got it done. And this is in 2016, I want to point out. So there was a lot of discussion that these self-driving taxis had showed up, that you could hail them, that they were there, that the services had started being rolled out. And I was like, okay, I get it. And so I'll come back to that later, but I think one of the things that's important is that that story did not end in 2016, and it still seems like it's not where we thought it was. Another thing that's people really highlight or kind of think is going to be an interesting dynamic of this is this notion of recovering urban space. But again, this is a thing that is afforded to you if you're able to remove the driver from the vehicle. So if we're able to take the driver completely out of the vehicle, you can think of some different models for dense urban areas. So this is an infographic I got from Mother Jones. And what they highlight here is just sort of the size of different things relative to parking spaces. And so if you look at a 2-bedroom apartment, that's about the equivalent of 1.5 parking spaces. And then if you look at a 6,000-foot church or 4,000-foot sanctuary, that's about the equivalent of a 90 parking space area. And so one of the things I think is really interesting about that is that we have all of this downtown urban area that is dedicated to parking or to having cars or these big assets that we need to have to move people from point to point left in a location. And so one of the things that people get really excited about is this notion that we could reclaim lots of this urban space if we're able to eliminate street parking. And again, how would this work in practice? Well, what it would mean is that you would have your car or your autonomous vehicle, loiter in some area and then come pick you up when it needed to pick you up, but it didn't have to be left somewhere, and certainly didn't have to be left somewhere in the highest value real estate area that was there. But again, all the things and all the sort of utopian ideals we hear about this require you to not have a driver in the vehicle. Otherwise, you just have a really, really expensive taxi. And so one of the things that is still interesting here is the sensors that I've been talking about that are on the vehicles, the things that are really kind of driving the self-driving car revolution in some ways, right now are also really expensive. So those spinning mirror LiDARs, particularly the really, really high resolution ones, those can be upwards of $90,000, $100,000. And so we have a couple, we put one on each roof of our vehicle, but now we take a base car that may have been $40,000, $50,000, and you add $150,000, $200,000 in sensors to it, and you're now at a point where that's a resource that you need to amortize that cost across as many people as possible. So the model of private ownership, at least in the near term, seems unrealistic. Now, 10, 15 years from now, perhaps, but to make the numbers work, you would have to share that. And so far, ride sharing or some model in which that resource is shared among as many people as possible, such that the downtime of that vehicle is as low as possible, seems like one of the few cases where you could make the numbers sort of start to work out. So where do I see areas for innovation before I get a little more pessimistic again? So why do I think that there will be some things that will work? Well, a couple things that I think is that a lot of this technology that's been developed for the fully autonomous, no driver in there robotaxi actually has a lot of other applications. And as I was saying before, I think that there's some parts of that we have solved, particularly highway driving or scenarios where you don't have to worry too much about unprotected pedestrians like cyclists or walking pedestrians. And so to that point, I think these delivery robots or these small robots that we see that use a lot of this same technology probably have a space to be successful because the risk for fatality is very low there. So you can make those actually driverless. Like you don't need to have someone in them because if they hit somebody, they're not going to kill them. The robotaxis are a little different because you need somebody watching over those so far simply because we don't have any systems that are fail-proof at this point. And so I think that there's going to be some kind of room for improvement around these sort of smaller technologies, or at least mid-sized technologies that run at a speed and at a weight that means that they can be deployed without drivers and make those economics work out. Okay, so let's talk about some of the things that I have seen that make me scared. So this is a video that I took from a keynote that NVIDIA gave, and I'm not trying to pick on NVIDIA. If anybody's from NVIDIA, I'm not trying to pick on you guys. It was just something they chose to show publicly, and so I thought, okay, let's look and see kind of where they think the state of the art is, what the best they have to offer that they want to show their shareholders. So they've been pushing a lot on autonomous driving, how it's going to be a big use of their video cards and other things. But they showed this. And if you look at it for a second, that looks good. They're detecting cars, great. But then if you pause it like I did, you start to see, okay, well, we're missing that white car. We're also missing that gray car. And I thought, that's not good. You don't want to be missing cars. And then I thought about, okay, well, let's see. Maybe it's just, bad luck here. We'll keep playing. Now, bear in mind, this is a slowed down version of what they showed at the keynote. I didn't stick it to them. I didn't pull out any cars. This is just what they chose to show. And you keep going. You see, well, actually, it misses that car. It's missing all the cars on the other side of the street here. And then it drops that car out. It's dropping that car out. Now, look, there are a lot of things that you can put on top of a technology like this. Tracking, additional sensor modalities, all those kind of things. But this is over a 30-second clip. You can see how many mistakes are being made here. Now, I think if you put a tracking algorithm on this, you get it all right. This is another example they showed from that same keynote. Okay, it's getting that police car right there, but it's missing that truck over there, okay, it gets it finally, but it's pretty far away. That car is completely missed. And then at some point it decides that's also a police car. It's not. And again, this was at a public event. So one of the things that this kind of brought to mind is when we look at the same data, so we have lots of machine learning that we run on their lovely cards, and if they're listening, please give us more. But one of the things that is really difficult is that where we are with deep learning is huge advances. So to think that we could have this level of accuracy even 10 years ago was unthinkable with the machine learning approach. And so we are really, really far from where we were. But one of the challenges is we're nowhere near 100%, and we may be really close to 99%, but the difference between 99 and 100, particularly if you think about over 100 million miles, is significant. And so one of the biggest challenges we're going to have is how do we get from 99%, or a thing we could show at a keynote when it's not actually driving, to something that you would trust to put yourself in front of, to put your children in, to put your family in, whatever. And one of the things that I like to highlight is that, so as an academic, we write papers on some machine learning approach. So you publish it at your favorite conference, and I've been going to those conferences for, I don't know, since I've been an academic. And a friend of mine asked me, he says, have you ever seen a paper in those conferences with 100% accuracy on any task? And I was like, no, I don't think I have, right? Maybe 99% on some simple tasks, but on complex tasks, nowhere near 100%. And what we're asking of our machine learning systems, at least if we're going to deploy them in a safety critical application, is we're going to have to be pretty near 100%, or it's certainly near 99 with a lot of nines at the end, if we're going to deploy them in things that are going to risk people's lives. And so I think that's one of the major challenges that we're going to face. This is an example of some of the kind of failures that we've had so far. So this is the Waymo vehicle slamming into a bus and the bus driver freaking out. He wants to know what's going on. But again, it's a great example of, in the limited vehicle testing we've been doing so far, we've seen a number of incidents, right? So there are a number of incidents on record, and in fact, many companies have pushed to do testing in environments where they have to do more limited reporting because of the number of interventions and incidents that happen that sort of may not rise to the level of something that is an accident, but if you had 100 million of these things on the road, you'd have to start thinking about. Another thing I think that's interesting, or perhaps going to be transformative in some ways, is there really is like a price trade-off between the idea of if we're going to have our vehicle loitering around as opposed to going to some place, dropping us off, and then going home. There's some point at which you could have a vehicle, or you could imagine that parking is not a thing that you need any longer, that it's actually more worthwhile to have the vehicle idle and just drive around, wait for you, and then come back, which we're kind of talking about the green space reclamation. But if you want to think some of the challenges of that, one of the things that self-driving cars are offered or proffered to do would be to help with the issue of traffic. But for this model to work, now we have many more cars on the road than we did before, right? Because we're taking the cars off the parking places and we're just putting them in the traffic spaces. So that means that to some degree, maybe now it takes longer to move through dense urban areas, even if it's cheaper. The second thing I'll hit, right, is that there's been a lot of discussion around, we're putting cars on the road without safety drivers. So again, I read the newspaper. I was like, man, wow, things have gotten a lot further than I thought. So this was the one that really hit me. I was like, this was in 2017, and they said that they'd pulled their safety drivers from the Waymo vehicles. And I really took a step back because I thought, oh, maybe the approach that we have is wrong, and maybe all the things that I've been saying are wrong, and maybe I don't get it, and maybe everything is actually solved. And so in Arizona, and again, Arizona is a very different environment than other places, right? The roads are really wide, the weather is insanely hot, so nobody walks around because it's insanely hot. It's sort of like here, I guess. The streets are really well maintained. There's no rain, there's no snow. Everybody drives super slow. I'm from New York, at least. Everybody drives super slow relative to how I drive. And so it seems like, okay, they picked a really benign environment, but they'd actually solved it. And then one of the things that came to mind really quickly was that I'd never met anyone who had seen a Waymo car without a safety driver in it. I'd never talked to anyone who had seen one without a safety driver in it. And then when news reports started coming out, it became clear that, in fact, there were not as many vehicles, or perhaps any vehicles, without safety drivers in them continuing, and that all of the people that they had pulled out got put back in. So I think this notion that we had solved this, or it was done, I think was sort of upended to some degree, for me at least at that point. So then people stopped talking. So a lot of the people that used to tell me what they were doing or how things were going or where things were stopped talking to me and stopped telling me how things were going, stopped making reports about what the vehicles were doing, stopped even listing sort of how many miles they had done. And one of the things I think is interesting about that is that there was sort of a large arc around what we thought this was going to be and where it was going to be. And one of the things that I want to use this talk to do is say that while I think the expectations were set sort of inappropriately at some point, I don't think we need to throw everything away that's already happened. So I know some people I talk to are really, really frustrated, like, this is never happening now, 20, 30 years. And I'm not convinced of that any longer. But I am convinced that sort of this approach that we're going to have press releases and bring some reporters and put them in our car and do one loop of a road and show them that it's doable. Well, that's a thing that we could do in 96, right? And so in 96, that was really impressive. That blew me away. But I think we need to hold people accountable more to do more. Like, we need to ask for more. We need to understand how many miles you're doing, in what conditions. We need to understand how safe those miles are. We understand how many interventions are happening. But even interventions themselves, or when the people take over, isn't really a clear reporting of exactly what's happening. So one of the things I'm hoping, and we'll see, is that people are pushing for sort of testing regimes that have clarity, that cut across the industry, and that are more transparent, at least to the public, or at least certainly to regulators that are going to be trying to figure out how do we put these things on the road safely. And so one of the things that I'm advocating for is just we have greater transparency from all the companies that are doing this, and we ask the government to have greater transparency with us in terms of the way they're regulating this. So they're in the same boat that I am. They talk to the companies tell them some things. They don't really have another way to go right now because the regulation doesn't exist for them to do anything but just sort of ask for reporting in whatever way the companies see as fit. So again, now if you keep abreast of the news, you'll see lots of reports or lots of discussion of sort of where a lot of the original hype or where a lot of the things that people were kind of pitching us 5, 6 years ago sort of haven't come to pass. But what I'm hoping is that sort of a lot of the technology that's been developed, particularly around highway driving and around lower speed vehicles, we see starting to filter to the market. So I am thinking that in the next couple of years, you will see robots in your daily lives. I don't think you'll be able to get into an autonomous taxi with no safety driver in it, at least in most of the parts of the United States that I can imagine. Maybe in some really restrained environments in Arizona, maybe in California, some places. But what I'm hoping is that some of those pieces of technology, particularly around highway driving, that we start to get autonomous trucks, because I think autonomous trucking around autonomous trucks around full-size autonomy, I think is doable on the highways. Things like low-speed vehicles, I think will be doable. And so again, I think we're going to start to see some of those play out. And again, if you just keep on it, there's lots of people that said a lot of things and weren't able to deliver. And last year was a bad year, I think, for people saying that things were going to happen. So I guess the last thing I want to leave you with, and then open it up for questions, because hopefully you have questions about all of the negative things that I've said. I think we're somewhere on this curve of this hype cycle. And so what I'm hoping is that we're somehow not going to kind of wallow in this trough of disillusionment, but we're going to figure out some way of using this technology effectively. And so you can see lots of things on here that at some point people are really excited about or are still really excited about. People are picking on augmented reality, but I guess people are still excited about that, but certainly not as much as they were when they were pouring tens of millions of dollars into companies that never did anything. But I think that we're really going to see something coming out of this level 4, which is that driverless autonomous vehicles, in the next couple of years. And we're going to see it not in the way that it was promised to us, but I think we're going to see it in some other way. Perhaps it's different. So I'll stop there. And if you guys have any questions, thanks.